Stars, by definition, are astronomical objects consisting of luminous spheroids of plasma held together by their own gravity. They store most of the baryonic matter that forms galaxies, and by assuming that there are 100 billion stars per galaxy, we can say that there are approximately 1 billion trillion stars in the observable universe. This extremely huge number reflects the possibility that stars exist in numerous shapes, sizes, and states, and these varieties determine the fate of any star, since we all know the fact that all stars evolve through the course of their lives. There are two main physical levels that govern the dynamical behavior of stars, both on the macroscopic and microscopic levels. On the macroscopic level, the main factors that influence the star are gravity, energy transportation through gas, and macroscopic gas dynamics. However, on the microscopic level, the main factors are nuclear fusion, the physical state of the gas, the chemical composition of the internal structure, and the way it affects energy transportation via radiation and convection. Curious to learn more about the dynamics of stellar evolution? Keep watching. Star formation. Stars form inside what's known as molecular clouds. They are relatively dense regions of interstellar gas and dust with extremely cold temperatures, at which the interstellar gas becomes of molecular form. In other words, the gaseous atoms bind together to form molecules, and that's why these clouds are referred to as molecular clouds. The most common molecules inside these clouds are carbon monoxide and hydrogen, and the extreme cold temperatures make the gas molecules form clusters of high densities. The star forms eventually when these densities reach a certain limit. The density of these regions makes them opaque to visible light, and that's why they're called dark nebula. In order to observe or investigate them, astronomers use infrared and radio telescopes. The beginning of the star formation happens when the denser parts of the dark nebula core collapse under the effect of their own gravity. The masses of these cores reach approximately 10 to the power 4 solar masses, and they are mainly in the form of gas and dust. Bearing in mind that the core of the dark nebula is more dense than the outer cloud itself, it's obvious that the cores collapse first. As the inner cores collapse under the effect of their own gravity, they disintegrate into clusters that are approximately 0.1 parsecs in diameter, and from 10 to 50 solar masses. Afterwards, the clusters form protostars, in a process that takes around 10 million years. You may ask yourself, how do astronomers know these facts if the star's birth takes place in the center of a dark nebula, which is opaque to visible light? And the answer simply is, most of the dark nebula cores have infrared sources, which constitute evidence of energy released from protostar collisions. Moreover, young stars are usually discovered with clouds of gas surrounding them, which are the dark nebula leftovers. Protostars. Once a dust cluster has freely disintegrated from the dark nebula core, it becomes a gravitationally bound body with its unique gravity and characteristics, and it's called a protostar. Loose gas falls into the center of the protostar during its formation. Kinetic energy is released in a form of heat by this infalling gas, causing the temperature and pressure of the protostar center to go up. At a certain point, when the central temperature reaches thousands of degrees, the protostar becomes an infrared source of energy. With the help of the Hubble Space Telescope, there are several candidate protostars that have been discovered in the Orion Nebula. Within the initial collapse of the dust cluster, the cluster is transparent, and the time interval of the collapse is relatively short. However, as the cluster adequates its own gravity, it becomes more dense and thereby more opaque to several types of radiation, one of which is the infrared radiation trapped inside the dense cluster and increasing the temperature and pressure of the core. At some point, the internal pressure stops the loose gas from falling into the center of the core. Therefore, the protostar becomes more stable as the dynamical equilibrium between the internal pressure and the infalling gas is achieved. The protostar has only about 1% of the total mass of the main sequence star. However, the star's envelope keeps growing from the infalling material, which is easily accreted because of the angular momentum of the protostar that turns it from an irregular shape to a rotating disk. So far, the protostar is governed by the macroscopic level factors mentioned in the introduction. However, the nuclear fusion takes place at the center of the core after a few million years. This nuclear fusion causes strong stellar winds to form, which in turn stops the infall of additional material into the protostar. At that point, when the protostar has a fixed mass, it can be considered a young star that evolves according to a typical scenario. Usually, the stellar wind forms along the axis of rotation of the young star, forming the so-called bipolar outflows, which are the flows of gas and dust being pushed out of the star poles. The bipolar flow is a feature that can easily be observed by radio telescopes. Additionally, it's the main feature of the star's early life, which is called the T-Tauri phase. The T-Tauri phase of a star has some characteristics, such as powerful surface activity in the form of flares or eruptions, strong stellar winds, and irregular light curves. Moreover, stars in the T-Tauri phase can be considered as pre-main sequence stars due to the fact that they lose up to 50% of their masses before settling down as main sequence stars. They begin their lives as relatively cool stars which heat up, become blue, and slightly vague afterwards. In general, the more massive a star is, the shorter its life. Therefore, various massive young stars are born with very short T-Tauri phases that are hard to observe. Before moving on, be sure to like or dislike the video so that we can continue to improve our content and make these videos better for you. Plus, be sure to subscribe to the channel and don't forget to hit the bell button so that you don't miss any of our weekly videos. The fate of any star is determined by its initial mass. We will list the different scenarios according to the initial mass of the star. 1. If the initial mass is less than 0.08 solar masses, the internal temperature and pressure of the protostar is insufficient to induce thermonuclear fusion that is necessary to fuse hydrogen into helium, which makes the protostar a failed star, and it's called a brown dwarf, midway between Jupiter and any regular star. To illustrate this, stars radiate light and energy due to the fusion of hydrogen into helium in their core. However, the temperature of the core must be at least 3 million Kelvin for the nuclear fusion to occur. And due to the fact that the core temperature increases with increasing gravitational pressure, the mass of the protostar must be at least 75 Jovian masses, or 0.08 solar masses. The dwarf star barely marks that limit. It's more massive than any observed supergiant gas planets and not massive enough to be a star. 2. If the initial mass is between 0.08 and 0.4 solar masses, then the star will be a very low-mass star that's too cool to fuse helium into carbon and oxygen. It will end up as a white dwarf made of helium. 3. If the initial mass is between 0.4 and 4 solar masses, then the star will be a fairly low star that's too cool to fuse carbon and oxygen into heavier elements. It will end up as a white dwarf made of carbon and oxygen. 4. If the initial mass is more than 4 solar masses, then the star will be a very massive star that's hot enough to fuse carbon and oxygen into heavier elements. It will qualify as a supergiant, which has a central core of iron towards the end of its life. That iron core is surrounded by shells of silicon, oxygen, carbon, helium, and hydrogen respectively. While the temperature in the center is extremely high, neutrinos are the carriers of the energy generated in the center of the supergiant, causing the energy of the iron core to bleed away. Eventually, the degeneracy pressure of electrons will not support the supergiant against the gravitational collapse of the core, which happens usually in less than 1 second, and the supergiant star ends with a violent explosion called a supernova, whose dynamics is very complicated, but we will try to briefly explain it. The iron core keeps collapsing on itself due to its gravitational pull until its density reaches around 400 million tons per cubic centimeter. At this certain point, the collapsed core resists any further compression and bounces back, producing a shock wave carried through the outer layers of the supergiant and heating them up due to the flow of neutrinos. The shock wave causes the gas in the outer layers to expand at a very high speed that is roughly 5% of the speed of light. Eventually, the rapid collapse of the iron core triggers the explosion of the shocked heated gas, and this explosion is known as supernova. Supernova are rare events due to the fact that they happen on average about one time every 100 years in our galaxy. And even though light is nothing more than a minor byproduct of the supernova explosion, the maximum luminosity of a typical supernova is 1 billion and 4 billion solar luminosities. This typical luminosity fails steadily after reaching the peak point and dropping by a factor of 100 every few months. Chinese astronomers observed the appearance of a guest star in the constellation Taurus on July 5, 1054 AD. That guest star was visible in daylight for 2 weeks and at night for 2 years before fading away. The position of this gas star nowadays is the location of the Crab Nebula, which is approximately 6,500 light-years from Earth. The Crab Nebula is a perfect example of a supernova remnant, which is the matter ejected in a supernova. The last observed supernova in our galaxy was Kepler's supernova, discovered by Johannes Kepler in 1604 AD. However, SN 1987A was the most recent naked-eye supernova located in the Large Magellanic Cloud, which is a dwarf satellite galaxy that orbits the Milky Way. In conclusion, stars are very dynamical objects whose behaviors are governed by many macroscopic and microscopic features. At first, gravity pushes the conditions inside stars into extreme regimes of high temperature and pressure, which in turn trigger the thermonuclear fusion of the core material within the limits of the nuclear force. The dynamical equilibrium of the star is achieved when there is a continuous adjustment between the gravitational pull of the core and the degeneracy pressure of the electrons. The more massive the star is, the shorter its life cycle, causing it to have an extremely short T-Tauri phase that cannot be observed to some extent. The fate of the star is ultimately governed by its initial mass. It will be a brown dwarf if its mass is less than 0.08 solar masses, meaning that it will be a failed star. If it exceeds 0.08 solar masses, it will end up as a white dwarf, whose chemical composition depends on the mass as well, or a supergiant, which will end up in a powerful explosion called the supernova, which is a rare luminous and temporal event. Thanks for watching, everyone. Can you state the stellar evolution in a form of steps? Have you learned anything new from this video? Let me know in the comments below. Be sure to subscribe, and I'll see you next time on the channel.